Hi, so I'm just going to go over a few more problems for Math 241 test number 3. Okay, so in 6.7 we have number 4. Okay, on page 211. Okay, so number 4 says use Chebyshev's inequality to estimate the probability that in any one day the first businessman of exercise 3 of section 6.5 will make either less than $60 or more than $140 profit. Okay, so it also says estimate the probability for the same event for the second business. Let's focus on the first business because the second, you'll do the same thing for the second business. So I'm going to let X equal to the profit in one day in dollars, and that's for business 1. Okay, so for business 1, X is the profit in one day in dollars for business 1. Okay, and so we want to know is what is the probability that X is less than 60 or X is greater than 140? That's what the probability is, right? Well, this is equal to the probability that the absolute value of X minus 100 is greater than 40. Okay, so X being less than 60 or greater than 140 means that's the absolute value of X minus 100 is greater than 40. And so that's equal to, this is a continuous random variable. And so I can just go ahead and say that this is the same as the probability the absolute value of X minus 100 is greater than or equal to 40. And include the equal sign there, and that won't change anything. And then this is then, by Chebyshev's inequality, this is less than or equal to e of x squared over 100, and that's because Chebyshev's inequality says the probability of absolute value of x of the probability of the absolute value of x is greater or equal to c is less than or equal to e of x squared over c squared. Okay, so what we have here is actually that the probability of the absolute value of x minus 100 is greater than or equal to c is less than or equal to e of x minus 100 squared over c squared. Okay, because here the variable here is x, and you put the x there and you square it. Here it's x minus 100, and so you're going to square x minus 100. This is less than or equal to e of x minus 100 squared over c squared, where c is 40. And so that's going to be over 40 squared. Okay? Okay, so now we just need to find e of x minus 100 squared. Well, the variance, lambda squared is the variance of x. Actually, wait, this is, okay, actually, so they also tell us that sigma, the standard deviation, is 28.87. So let me try something else. Let me do this. This is equal to the probability that the absolute value of so x is less than 60. So let's do x minus mu here is 100. X minus mu over sigma is less than 60, or x is greater than or x minus minus mu over sigma is greater than 140. And so then this will be equal to the probability that the absolute value of x minus mu over sigma is greater than 40. And that will equal to the probability the absolute value of x minus mu over sigma is going to equal to 40. But because mu is 100 and sigma is 28.87, this is the probability. This is the probability that this is 60 minus mu over sigma. This is 140 minus mu over sigma. And so then this is going to be so this 60 minus mu over sigma is negative 40 over 28.87, and this is going to be 40 over 28.87, and so this is going to be greater than 40 over 28.87, and greater or equal to 40 over 28.87. So that's z. This is the probability that the absolute value of z is going to equal to 40 over 28.87. And so by Chebyshev's inequality, this is less or equal to e of z squared over c squared, where that's c. And so this is 40 over 28.87 squared. Okay, and so the variance of z. So the variance of z, because z is the standard normal. The variance of z is going to equal 1, and so the variance of z is also equal to e of z squared minus e squared of z, but also the mu here of z is 0. And so that's 0. So this is equal to e of z squared minus 0 squared. And that's the variance of z, which is 1. And so that means that e of z squared is also equal to 1. And so that's 1. And so this is 1 over that, which is the same as 28.87 over 40 in parentheses squared. And so you could square that fraction, and that's an upper bound of that by Chebyshev's inequality. So this is less or equal to that by Chebyshev's inequality. Okay? Okay, and so we get that as our answer. Okay, so let's keep going. So that's number 4 there. Next one. Okay, 6.8 number 1 is the next one we're going to look at. And so 6.8 number 1 is on page 215 to 217, specifically to page 215. And so number 1 says, what is the expected number of 6s in 30 rolls of a balanced die? What is the standard deviation? So E of x is defined to be the sum over x of x times f of x, right? And so in this case, if we're rolling a die 30 times, right? So if we have a die here and we roll it 30 times, right? So the question is, how many times could you get a 6? Well, the possible number of times to get a 6 if you roll the die 30 times is 0 through 30. You could get it. You could We get 0 times up to including 30 times. X is going to be the number of 6s in 30 dice rolls. Okay, so the value of x is going to range from 0 to 30, and we're going to sum the values of x times f of x. So what's the probability of f of x? F of x is the probability that you roll x 6s in 30 dice rolls. Okay, and so what that probability is it's 30 choose x times 1/6 the x times 5/6 to the 30 minus x. It's a binomial distribution. If we're rolling 6x 6s, the probability of rolling a 6 is 1/6, and so you multiply 1/6 x times. But then the probability of not getting a 6 is 5/6, and so if you roll the 6x times, you would not roll 6 30 minus x times, and so you would multiply 1/6 the x times 5/6 to the 30 minus x. That would be the number of times of rolling, let's say, a 6 in the first x rolls, and then not a 6 in the remaining 30 minus x rolls. You could take that and you could rearrange it 30 choose x ways. And so if x of those rolls are 6s and 30 minus x are not 6s, but specifically x of the 30 rolls are 6s, there would be 30 choose x ways of arranging it so that in the 30 rolls, x of them are 6s and 30 minus x are not. And so the probability f of x is equal to that, and that's called the binomial distribution. Okay, and so f of x here is that, and so I'm going to substitute that here. It says 30 choose x, 1/6 the x times 5/6 to 30 minus x. And so e of x is equal to that. Okay, and so you could calculate that sum and you get e of x. Now e of x squared is just the sum, it's almost the same thing, x equals 0 to 30, but instead of x here it's x squared, and then you still multiply by 30, choose x. Here, 1/6 the x, and 5/6 to 30 minus x. And that's e of x squared. Okay? And so then that would be that, and then if you want to find the variance in this situation, the variance of x would be e of x squared minus e squared of x, or e of x squared. And so you just take this value and you subtract the square of that value, and you would find the variance. Okay, so that's 6.8, number 1. So 6.9.2, numbers 1 and 3. So number 1 in 6.9.2, so for number 1, it says x is a random variable. So x is a random variable, the normal distribution, with mean mu is equal to 2, and standard deviation sigma equals 0.5. Find the probability that in part A, find the probability that x takes on a value greater than 3. So what is the probability that x is greater than 3? Well, that's equal to the probability that x minus mu over sigma is greater than 3 minus mu over sigma. That's equal to the probability of x. Well, x minus mu over sigma is z, the standard normal variable, and so that's z. And then 3 minus mu over sigma is 3 minus 2 over 0.5. And so that's equal to the probability that z is greater than 1 over 1/2, which is 2. So that's the probability that z is greater than 2. That's equal to 1/2. So I guess I could be more specific. 1 minus the probability that z is less or equal to 2. And that's equal to 1 minus 1/2 plus the probability that 0 is less than z, less than 2. Okay, and so then that's equal to 1/2 minus the probability of 0 less than z, less than 2. And so if you find this probability in the table, you get that that's probability is 0.4772. So this is 0.5 minus 0.4772. That's equal to 0.0228. And that's the answer. Okay? So that's 6.9.2, number 1. Okay. So so 6.10.2, number 1. So 6.10.2, number 1, 223. Exercises 1. How might you estimate the average income of residents of a very large city without finding the income of every resident? What theorem may be used to justify the method? So for number 1 in this page, the strong law of large numbers lets us conclude that we can estimate the average income of residents of a large community, of a very large community, by finding the average income of a very large subset of these residents. Okay, so if you choose a very large subset of the residents and you find the average income from those people, then that is a good estimate, a very good estimate for the average income for everyone in the neighborhood. That's by the strong law of large numbers lets you say that. Okay, so that's 6.10.2, number 1. Okay, so 7.2.7, and so there's a bunch of problems in this section. We're going to focus on number 1. There's also these problems, so I'm not saying there are more problems. Okay, so the number 1 here, so 7.2.7, let's look at number 1. And so number 1 says, consider the experiment of a single roll of a die and a single toss of 3 coins. So x1 would be the value of the die, and x2 would be the number of heads. Find the joint probability function of x1, x2. That's in your book. That's page 249, number 1. So x1 is going to equal the value of a roll of 1 die. x2 is going to equal the number of heads of 3 coin flips. Okay, so x1 is the value of a roll of 1 die, x2 is the number of heads of 3 coin flips. And so the goal is to find the joint probability function of x1 and x2. That's the same in notation as f of x1 comma x2. That's the joint probability function of x1 and x2. We're using the word joint because there's 2. We might use the word multivariate, but when there's 2, you would use the word joint instead. Okay, so here, x1 and x2 are independent events. Right? They're independent events because they're 2 experiments that are completely different. Right? And so in class we went over, when you have 2 completely different experiments, neither the outcomes for both experiments do not depend on the other one. So they're independent events. And so that implies that f of x1 comma x2 is equal to f sub 1 of x1 times f sub 2 of x2. Okay? And so we're going to find the joint probability function of x1 and x2 by finding f sub 1 of x1, f sub 2 of x2, and multiplying them. And by this equation, we'll know what f of x1 comma x2 is. Okay? So f sub 1 of x1 is just the probability of each roll of the die. So that's 1/6 for every possible roll of the die, which is for x1 equals 1, 2, 3, 4, 5, 6. Right? The probability of any roll of the die is 1/6. So f sub 1 of x1 is 1/6 for x1 from 1 to 6. F sub 2 of x2 is the probability of the number of heads you would get in 3 coin flips. Well, the number of heads you could have are x2 is equal to 0, x2 is equal to 1, x2 is equal to 2, and x2 is equal to 3. x2 number of heads in 3 coin flips. If you flip a coin 3 times, you could have 0, 1, 2, or 3 total heads in the 3 coin flips. So the probability that there's 0 heads is just the probability that there are tails every time. So there's 1/2 probability each time for tails, and so there's 3 flips, so 1/2 times 1/2 times 1/2, and that's 1/8. The probability of 1 heads is 3/8. That's because you could have So for every arrangement of heads and tails, there's 1/8 probability, and one way to think of it is if you have one heads, you could have the first one as heads, the other two tails, the second one is heads, the other two tails, the third one is tails, the other two heads, the other two tails. So there's 3 ways to have one heads and 2 tails, and each one has a probability of 1/8, so that's 3/8 probability. Very similarly, the probability of exactly 2 heads would be the probability that 2 are heads and 1 is tails. So instead of thinking 2 heads, you could just think the probability of there one being 1 tails. And so the first one would be tails, the second one would be tails, the third one would be tails. So there's 3 total situations where there's 2 heads and 1 tails. And so each one is probably 1/8, so it's total 3/8. And then the probability of being 3 heads is just the probability of what every flip is a head. That's 1/2 times 1/2 times 1/2, which is 1/8. Okay, so that's the probability of f. This is f sub 2 of x2. Okay, this piecewise function. 1/8 for x2 equals 0, 3/8 for x2 equals 1, 3/8 for x2 equals 2, and 1/8 for x2 equals 3. And so to find the joint probability function, that's equal to f sub 1 of x1 times f sub 2 of x2, because x1 and x2 are independent events. And so that's equal to this function times that one. Well, this is always 1/6, so I'm just going to multiply these things by 1/6. And so I'm going to get 1/8 times 1/6 is 1/48. But this is for not only x2 is equal to 0, but also x2 is equal to 3. And then 3/8 is for both of these, multiply that 1/6, and you get 3/48. And that's for x2 is equal to 1 or 2. And then this is for, and then this also includes every x value, x1 value, right, from 1 to 6. That includes every x1 value from 1 to 6. And so now here, this is the joint probability function of x and y right there. And that's the answer. Okay, so that's the answer to number 1 in 7.2.7. Okay, so let's keep going. Okay, so 7.2.7 number 6. Okay, so for number 6 and 7.2.7, same section, we'll let x and y be continuous random variables with joint cumulative distribution function there. So it's given to you in the book on page 250, so refer to that when I'm answering this question. 6a, it says, find the probability of each of the following events that both random variables take on values that are less or equal to 0.5. And so that means it's capital F of 0.5 comma 0.5. This is the probability that x is at most 0.5 and y is at most 0.5. And so you just plug that into the function they give you here. And so you have to choose x squared, y squared for x and y between 0 and 1. And just plug in 0.5 for x and y. And so you get 0.5 squared times 0.5 squared, which is 1/2 squared times 1/2 squared, which is 1/16. And that's equal to 0.0625. Okay, so that's 1/16. So that's A. And B, x takes on a value that is less than or equal to 0.5. Y takes on a value that is not greater than 0.5. So if x is less than or equal to 0.5, it's at most 0.5. So I put a 0.5 there. And if x is not greater than 0.5, if y is not greater than 0.75, it's less or equal to 0.75, so it's at most 0.75. And so you use the same formula here, 0.5 squared times 0.75 squared, and so you get 9/16. That's equal to 9/16, which is 0.5525. Okay? And so that's 6AB. Okay, so now 7.3.3, numbers 1, 6, and 7 in this section. And so let's focus on page 259. And so numbers 1, 6, and 7. So let's focus on number 1. Okay? So here the probability function, joint probability function of x and y is given as being, so the question is, are the random variables of exercise 9 in section 7.2 independent random variables explained? So here's the joint probability function of x and y for that example. It's 4 nines xy for x strictly between 1 and 2, and y strictly between 1 and 2, and it's 0 elsewhere. Okay, that's the joint probability function of x and y. And here x, y are continuous random variables. Okay? Okay, so f sub x of x is equal to the integral from negative infinity to infinity of f of x comma y, which is 4/9 xy dy. And so if you evaluate the definition, so actually here it's from negative infinity to infinity, but we see that the y values only go from 1 to 2. So we can actually restrict this from 1 to 2, 4/9 xy dy. And when you compute that definite integral, you'll get 2/3 x. Okay, and if you find f sub y of y, that's equal to the integral from negative infinity to infinity of 4/9 xy dx. And so now, well, x only goes from 1 to 2, so you can reduce the limits of integration from negative infinity to infinity instead to 1 to 2. And that's the definite integral from 1 to 2 of 4/9 xy dx. And if you compute that definite integral, you get 2/3 y. Okay, so f sub x of x is 2/3 x, and f sub y of y is 2/3 y. And so that means that we'll write up here, f sub x of x times f sub y of y is equal to that function, which is 2/3 x, times the other function, which is 2/3 y. And that's equal to 4/9 xy. 4/9 xy is f of x comma y. And actually, I should mention that this is for this is for x strictly between 1 to 2. And this is for y strictly between 1 to 2. And so this is equal to that for 1 less than x less than 2, 1 less than y less than 2. And they're both 0 everywhere else. And so we show that this function is equal to this function here and everywhere else. So they'll both be 0 everywhere else. And so because that equals that, x and y are independent variables. And so in 1, we prove x and y are independent variables by showing this times that is equal to that. So it concludes that x and y are independent variables from that. Okay, and so that's some more review problems for you to study. Watch these videos, watch them again if you need to, go over all these answers, do more problems on your own, and office hours if you need them. Okay, good luck studying.